Welcome everybody to RISE Learning Machines seminars. I am Olof Mogre. I'm a machine learning researcher at RISE, which is Sweden's public research institute. And this Learning Machines, that's our open weekly seminar on AI and machine learning. This particular meeting is organized in collaboration with Climate AI Nordics, a network of researchers applying AI to environmental and climate change related applications. The meeting will be recorded, and let us know if you want to be removed from this recording before we publish it on YouTube. And by the way, on YouTube, you can find a great number of recordings that we've done over the years. Today, I have the absolute pleasure to introduce Dr. María Molina, who is assistant professor at University of Maryland in the Department of Atmospheric and Oceanic Science. She's also affiliated with the Artificial Intelligence Interdisciplinary Institute and the Institute for Advanced Computer Studies. She defended her PhD at Florida International University in 2023, and she works on machine learning and numerical methods applied to climate and extreme weather studies. She focused this research on Earth system prediction, extreme event genesis, and multi-scale climate patterns. The topic of today's talk is machine learning for Earth system prediction and predictability. And with this said, I will hand over the floor to you, Maria.
Great, thank you so much. Okay, and can you see just fine? Okay, fantastic.
Yes, looks good.
I'll hide my, there we go. Okay, hello everybody. Thank you so much for taking the time to join today. It is afternoon over there. Today I'll be giving a talk on machine learning for Earth system prediction and predictability. And I have been at the University of Maryland now for a little more than 2 years and have been working in this research topic or general realm since approximately 2019. Have a direct path. So to share a little bit more about some of my earlier career and background before going to graduate school and becoming a researcher in the topic of AI at the intersection with geoscience topics. I actually worked in television, so I used to be a weather presenter on national cable news, and there were a number of extreme events that were that we covered across the United States, and some of these included very heavy snowfall. For example, here in the top left, there was an event that produced quite a lot of snow, and I'm realizing I'm giving you this in U.S. Metrics, which is 5 feet, but essentially that's about how tall I am in terms of snowfall total. There were also a number of extreme events like tornadoes across the country that produced quite a lot of damage, and so we got to witness these events many times, either firsthand or shortly after they occur. So it really sparked my interest even further in extreme weather, and also thinking about some of these events on a climate timescale and asking questions like, why are they so much more frequent during certain years, certain seasons? So thinking about climate variability, and then also long-term trends. Are they going to be occurring more frequently in certain parts of the world? So thinking about the external forcing issues. As a broadcaster, it was also important to extend a relationship or build a relationship with viewers to build the trust when the weather was good. And so I got to do a number of fun pieces where there were things like looking at weather testing of vehicles, and also just simply flying with a jet team here in the US, and essentially sort of poking fun of myself by having me pass out or do a number of other such activities where people could connect and again build that trust and that relationship when the weather was good, so that that relationship was established when the weather was bad. But I've been interested in extremes since I was a child. There was a very strong hurricane or tropical cyclone that impacted where I grew up in South Florida. And that event really kind of made me interested in extremes ever since then. And I've continued to have a bit of a windy path, but always consistently on the topic of extremes, and now working at the intersection of AI and also climate topics. I'm very fortunate to work with a team of students that are extremely inspiring and highly motivated and give me a lot of hope about the future. And so these are their faces, and you'll be seeing a lot of the work that they have been contributing to or that they have led since my time starting at the University of Maryland. But a little bit of background on AI, although I'm sure you are all experts on this topic, I just wanted to kind of set the stage on why we're so excited about machine learning and all of its potential for the physical sciences. So as we know, AI is not new. It's been around since the 1950s when it was first sort of established or recognized and defined as a field. And then eventually there were periods of extreme interest in the community and a lot of funding and excitement and perhaps some hype, like in the late 1950s and then also in the 80s. And there were also periods where some of the excitement waned and there was reduced funding for AI. And we tend to refer to these as AI winters. And that was like in the 70s and also more recently in approximately the 90s. But in the last couple of decades, it has been very exciting and an explosion. And this is due to a number of factors. I'm sure you all are familiar with GPUs. So GPUs really help us parallelize a lot of these matrix multiplications that happen when we're training our neural networks and then performing inference. And so that has accelerated the speed at which we can train these neural networks and advance our capability to train more complex neural networks that can perform very well. But then we also have very high quality, large data sets like ImageNet and a number of others that went on to become part of these challenges and benchmark competitions. And that really enabled organized community engagement and involvement to continue to develop and advance the field as a whole and improve performance on high quality and already pre-labeled data sets. And of course, open source software, tools, and development has also been very much a contributor to this explosion. So for example, if we think about some of the software that we might use, here I'm showing Keras and TensorFlow. More recently, Keras version 3 was released. And of course, also PyTorch and a number of other open source libraries and very dynamic community that has been built over decades as well has led to this community of support where if you have a question, you can ask someone online or you can see examples of code online. And again, just really facilitating this advancement of the science that we do and of the provision of these tools that are available to anyone that would like to use them. So again, just this intersection of all of these advances and different conditions have really created this environment that we're in, where we get to sort of stand on the shoulders of giants and continue to advance the field and have some fun doing applying neural networks to our questions. But when we think about the spectrum of machine learning methods, Usually when we mention neural networks, we're thinking specifically about deep learning when we have neural networks that are several layers deep. And that is primarily in an environment where we would be able to have a lot of data. So very large data sets would be, of course, best for a deep learning approach. And there are other approaches that we can use when we have fewer samples. So for example, symbolic regression, or also referred to as equation discovery, is a method that would work well when we have smaller data sets. So the size of our data set can, to some extent, dictate what sort of approach we can, or be a constraint to what sort of approach we can end up using in machine learning and the method or algorithm that we end up choosing. But there are also ways to get around this. For example, we can train a neural network in an area where we have a lot of data and then use a technique like transfer learning or meta learning to shift over to a regime where we have fewer samples. Of course, the more data we need, the less we have to rely on our domain knowledge. But in the physical science, there certainly is the importance of considering the physical knowledge that we have, and also use certain constraints when needed to ensure that our models are physically consistent. When we're thinking about climate modeling or weather prediction in a traditional sense, we can think of the workflow in 3 different stages. So for example, if we go ahead and get ready to run something like the Community Earth System model, from NCAR and also many developers that have contributed over decades, we can think of that workflow in these 3 stages. So first, we would have an input stage where we have to create some sort of initial state that represents the conditions of the atmosphere, or in this case, in the total Earth system. So the different components that make up the Earth system, such as ice, ocean, land, and so forth, in addition to the atmosphere. Then we would have the stage, once that's done, to actually begin running the numerical calculations and running the physical model forward in time. So this might involve the use of physics parameterization schemes, where we have simplified equations or algorithms that compute microphysics and other such processes that are not resolved or explicitly resolved, but are at the subgrid scale, and we go ahead and estimate and run those forward in time as well with the rest of the model. Once we're done running that model to the time scale that we're interested in, so that could be a number of days if we're talking about weather time-scales, or it could be decades in the future if we're interested in, for example, climate projections or multi-decadal prediction. Then we would stop running the model and we would handle our output. And in each one of these stages, we can actually go ahead and use machine learning for specific tasks. So for example, at the initial state, we can go ahead and perform data assimilation or parameter estimation using AI. We can also use techniques like active learning to determine where we would optimally place a new sensor, or let's say in situ weather station, if we had the opportunity to, and we want to minimize some sort of error or perhaps uncertainty. We also have machine learning that can be used in the running the model stage. So that could be potentially creating physical parameterization schemes that are more representative or more skillful or of subgrid scale processes. And it could also entail online bias correction as the numerical model is running forward in time. And we can also use machine learning at the output stage. So taking our output from our weather and or climate models and using it to either further downscale in spatial resolution, the output, or even performing offline bias correction, where we try to improve some of the output from the respective physical model. And of course, we don't really have to limit ourselves to these individual stages when we're talking about numerical weather and climate modeling. we can go ahead and simply use machine learning to bypass the entire running the model stage, and we can give it some input and then generate an output at the lead time of interest, or even generate it over time in a sort of autoregressive mode where we go ahead and take the output and stick it back as the input of the respective machine learning model over time. And this has led to a lot of excitement in recent years. Perhaps you recall the cover of Science. This was back in December 2023, where we saw GraphCast, DeepMind's GraphCast, make the cover of Science and show that there is quite a lot of potential to generate skillful forecasting for even extremes using purely data-driven modeling. And of course, we also need to consider the ethics of the machine learning algorithms that we are using. The data that we are using to train our models may contain some biases or other such issues of lack of representation. And while it's quite easy to think about examples in the real world or in industry applications, such as this face-to-pixelizer that essentially would take a coarsened image or headshot of a person and then generate a higher resolution version of it. And there was this viral tweet back when Twitter was generating tweets, and you likely can recognize a person on the left-hand side as Barack Obama, and his race was completely changed in the output of this facey pixelizer, illustrating one of the biases in this algorithm. And in our physical science data, we can also have issues in representation and biases, and these are really important to consider. So for example, we're seeing more and more extreme events, and some extreme events may not be present at all in our training data set. There was this tropical cyclone that made landfall along the Gulf of Mexico in the United States, and it ended up tracking northward and produced a lot of rainfall over the New York City area and left scenes like this that you're seeing on the right-hand side. And if you're not familiar with the geography of the US, New York City is very, very far away from Louisiana along the Gulf Coast. And so it was quite shocking to see some of these images from an event that made landfall so far away. So asking questions like, what does it mean if our training data is not representative of our changing climate? And can our models extrapolate to some of these previously unseen events and generate trustworthy results are questions that we, of course, need to ask ourselves, and many have been asking in recent years. But when we're using machine learning for Earth system modeling, we really need to consider asking questions of robustness that I just mentioned. So ensuring that our systems and our trained models are robust to non-stationary data distributions, and perhaps also consider some causality, and also incorporating our physics and domain knowledge, and that we can also interrogate our models. So whether that means using simpler machine learning models that are inherently interpretable, or whether that means taking a non-interpretable machine learning model and then applying algorithms after the fact, such as explainable machine learning tools, where we can ask, why did you generate such a prediction? There is a project that I wanted to highlight. This was led by Professor Amy Forcume at Howard University. This is in the Washington, D.C. area, not too far where I am based. And her work essentially uncovered that there are a number of biases in air quality data along the coastal areas in Louisiana in the United States, where there are a number of sensors that show good air quality conditions, but humans were experiencing not good air quality conditions. And so again, thinking about us training these very important models that are performing tasks that impact humans, and using data that may not be actually representative of what's on the ground could be potentially extremely problematic and something that we should consider. But now I'll go ahead and give you some very brief sort of vignettes of some machine learning applications that myself and others in my group and collaborators have been working on over the years. And just to show you some very quick examples of machine learning applications for weather and climate and associated extremes. So one of the very common applications, especially in a few years ago when machine learning applications in weather and climate were really getting going, is the detection of specific features within our data sets. So in this animation, you're seeing the detection of fronts within a climate model. This is a community or system model. And the different colors show different types of fronts, whether it's a cold front or a warm front. And what was really exciting about this work is that we took a deep learning model that was trained to detect these fronts in one data set. I believe it was a reanalysis data set, and then applied it to a climate model and were able to get climatologies of fronts that were realistic and consistent with observations. And we were also able to visually inspect the fields and note that they did indeed look like what we would expect fronts to look like. So that was really promising in terms of generalization from training in one setting with one data set and then performing inference on a different data set. We also have a project that actually just yesterday was accepted for publication. That's this citation here on the bottom, where we were performing global detection of mesoscale convective systems using a number of different trackers and a number of different kilometer scale global simulations from the Diamond project, and going ahead and comparing what the MCS statistics look like across the globe, both in different models and also in based on our different tracking schemes. And here we used a UNet architecture where we took in an image and then output a classification scheme or detection scheme for our machine learning based mesoscale convective systems. And what was really exciting about this work is that we trained with labels only over North America, because that is where we had labels of detected mesoscale convective systems. And we were then able to apply data augmentation techniques and a couple of tricks just to get the machine learning model to detect these events globally. And we were able to get it to do so with skill around the globe, and also very much with skill that was comparable to tracking algorithms that were tuned specifically to detect mesoscale convective systems across the globe. So again, two examples of detection of extremes or features, and also of the ability of machine learning to generalize, either simply by giving it a new data set and seeing how it performs, or by employing a number of techniques like data augmentation and also careful pre-processing of our data sets, including how we standardize and normalize our data sets so that we can go ahead and generalize across a more global domain. We can also design experiments to answer questions. For example, Jairon, a PhD student in my group, recently devised this study where he was curious about this schematic here on the left-hand side that shows that most of the predictability at the weather timescale comes from the atmosphere. Most of the predictability at lead times at the subseasonal timescale, so sort of beyond 10 days, but less than a month, come from the land. And then this schematic suggests that at longer timescales, so when we're thinking about seasonal timescales or beyond a month, most of the predictability comes from the ocean. So he went ahead and tested this schematic using some XGBoost, so a tree-based model, and generated classifications for weather regimes over North America, which are just large-scale 500 hectopascal geopotential height anomalies, and essentially was able to identify that there's actually quite a bit of seasonality to this relationship that we're seeing on this schematic. And this publication just had minor revisions, so it should be out in the wild soon, but it is also available on archive. And again, essentially showing that there is much more nuance to this schematic on the left-hand side than originally shown in the earlier studies. And we can also perform uncertainty quantification. So this is a study that was led by a computer science PhD student from the University of Maryland, where essentially he went ahead and used a diffusion model and a hypernetwork. So both of these are actually tethered together. And his question was, can we not only generate an ensemble distribution by leveraging the generative properties of a diffusion model, but can we also decompose the uncertainty into the aleatoric and epistemic pieces, where aleatoric is sort of, we can think of as uncertainty that can't really be reduced. It's inherent to the predictive task or the data sets, and epistemic being uncertainty that it can be potentially reduced if we had more examples of that respective event or type of event. And here, how this works is he goes ahead and generates or creates an input field. This is North America 2-meter air temperature. This goes into the diffusion model, and the hypernetwork generates an ensemble of network weights. And so these weights go into the diffusion model and generate a specific prediction. And if we generate an ensemble of weights, we can generate an ensemble of distributions. But we can also use the generative properties of the diffusion model to also generate spread. And so if we hold one of these fixed and add noise to the other, or vice versa, we can go ahead and decompose our uncertainty into these two different components. And this paper did come out. It came out in NeurIPS in December 2024. And I'd be happy to take questions on any of these other projects and applications at the end of the seminar. But I do want to transition over now to two projects a little bit more in depth on the topic of prediction and predictability. And those will be the slides that take me all the way to the end. So if we think about prediction and predictability, for prediction, we're talking about specifically the task of predicting something into some future lead time, or it can be an outlook generated for future conditions, whereas predictability really is the inherent upper limit for skillful prediction. So really that's just as good as it can get. Let's say, for example, if we had a perfect model. And if we think about this in sort of a very simplified schematic, the task of prediction out to some lead times of interest. The lead times of interest, I'll be focusing on our weeks 3 and 4 into the future. We know that our model, whether it's data-driven or physics-based, is going to have some error, and it's not going to align perfectly with observations, right? So there's going to be some deviation. And these model errors can have a number of sources. It can be due to our subgrid scale parameterization schemes, simply not being able to perfectly resolve processes in the Earth system, or it can also be due to initial condition errors that arise for us not being able to perfectly represent that initial state. And one of the ways that we approximate some of this uncertainty or error associated with our initial conditions is by generating an ensemble of predictions. So we can slightly perturb those initial conditions that we have and run them forward in time, and now generate a future probability density function or distribution of possible outcomes at a future lead time of interest. And we can sort of use this as some sort of uncertainty regarding how confident we are about our future prediction, given some uncertainty at the initial state. And so in this study, or both of these studies that I'll be sharing with you, we use the Community Earth System Model version 2, specifically the initialized subseasonal prediction system. So this was specifically created, or it's a modified version of CESM2 tuned specifically for the task of predicting out to about 46 days, producing data at the sub-daily temporal scale or cadence. And there is a 20-year hindcast, which is somewhat limited, but at least not too bad. And so we ended up using 15 years for training and 5 years for testing. And we focused on two tasks. The first I'll be sharing is the assessment of how skillful was CESM2 at generating North American weather regime predictions. And the next one will be the task of bias correction. But focusing first on the initial task, we decided to go ahead and focus on subseasonal prediction of large-scale patterns of the atmosphere over North America. So these are North American weather regimes. These are 500 hectopascal geopotential height anomalies, and the anomalies here are in meters. But essentially what we're seeing are some recurrent large-scale atmospheric patterns over North America that offer us some ability to simplify the prediction task into these large-scale patterns, but we know that depending on the amplitude and persistence of these patterns, we can end up seeing a signal at the surface in terms of either temperature anomalies, or in this example, some precipitation anomalies. So you can see that for the Alaskan Ridge regime, which is 21% of the total, this is the extended cool season frequency. And so here we can see that the Alaskan Ridge tends to have areas of drier conditions or wetter conditions, with wetter conditions really being dominant over the state of California, likely associated with incoming atmospheric rivers during the cool season. And we can take k-means clustering algorithm. So this is a very straightforward, simple machine learning model, and we can train it in a reanalysis setting. So in this case, we use ERA 5 to train the k-means clustering algorithm. Then we froze the centroids, so no longer we're training, but we gave it CESM data. And so we were interested in seeing whether or not CESM2 has some biases in its representation of North American weather regimes, not just as a whole, but as a function of lead time. And if we take a close look at weeks 3, 4, and then by weeks 5, 6, it becomes much more evident. There is actually an overoccurrence of the West Coast high regime here, this light gray shading, and an underoccurrence of the Greenland high and Alaskan ridge regimes. So we're seeing that we have a bias in CESM2, where, of course, near the initialization time, it is very closely aligned with the initial conditions. But then as we increase in lead time, we see this drift away of certain large-scale patterns from what they should be, according to ERA 5. And we decided to take a look at the uncertainty associated with these forecasts, and we anticipated that we would have a very small, initial perturbation of our initial states, and that would result in an increase in spread over time. But there were certain forecasts where we observed some pretty strange behavior, where we actually had an increase in spread at a certain lead time, and then over time, that spread decreased. So we were really curious about why this was happening. Did this just happen by chance? There's only so many weather regimes. Perhaps this is just some statistical fluke where we just happen to have some cases where this occurred and seemed to be meaningful, but really weren't. And so to get around this, we decided to look at some of the specific forecasts where this occurred. So in this example, I'm sharing with you November 9th, 2015 initialization. And on the x-axis, you're seeing lead time as a function of days. And on the y-axis, you're seeing how many ensemble members. There were only 11, so that would be the maximum. How many agreed on a specific forecast? And the way to interpret these little circles and X's is if they are the same color, that means the community Earth system model got the forecast right. the forecast being a specific North American weather regime. And if they're not the same color, then it got the forecast wrong. But you can see that for this specific forecast, during early lead times, there was a lot of agreements. Obviously, the forecast is correct. It's going to be very close to the initial condition. And over time, you see that ensemble agreement decreases and the forecast is wrong. But then suddenly by lead times of days 25 to 30 into the future, you start to see agreements of 8 ensemble members. It gets up to 9 ensemble members agreeing on, in this case, specific trough regime being the forecast and it being correct. And so we were like, did this happen by chance or is it actually meaningful? And so it turns out if we look at the outgoing long wave radiation skill being in comparison to ERA 5. On the y-axis, we have the anomaly correlation coefficient. We can see that for the black line, outgoing long wave radiation over the Indian Pacific Ocean was extremely skillful during all of the early lead times. And then over the North Pacific, we don't have good representation of that outgoing long wave radiation during those times where we have little ensemble agreements. But then by the time we get into lead days of 20 through 30, we see a lot of agreements in that pattern. And so essentially what we're seeing here is the propagation of Madden-Julian oscillation type outgoing long wave radiation patterns. So convection moving eastward from the Indian Pacific Ocean into the North Pacific, and the North Pacific involving the location of the Pacific trough regime. So this skill ends up showing up in our forecasts at these respective lead times with a lot of confidence and ensemble agreements. So we thought this was pretty interesting. Unfortunately, this does not happen often enough to yield a lot of excitement. And there are cases where you can get a lot of ensemble member agreement, but the forecast still be wrong. And of course, that being if the community or system model, for example, ended up creating some of these patterns in convection and Madden-Julian oscillation, but they weren't present in observations or vice versa. So it is something to not get too excited about, but it is an artifact that does happen. And since sharing this work with others, I've received confirmation that indeed others have noted this type of behavior in their respective models. And for example, I know that someone mentioned this in the NASA GEOS model, and others that have seen this type of behavior as well with tropical cyclone forecasting. But anyway, again, lots of caveats involved there, but that was kind of interesting to see. And then the other application I wanted to share is the task of offline bias correction. So earlier I showed this very simple schematic where we have a black line, that's our physics-based model. We know there's some error, but perhaps we can use bias correction after our physics-based model has been run, so offline, and nudge that simulation towards observations so that we can yield some improvement, hopefully, in our prediction. And so essentially, really what we're after is trying to learn with machine learning some systematic errors in our physics-based model that can be tested to reduce our error in our predictions at our lead time of interest. And so we thought this was a relatively straightforward machine learning task, and indeed it is, until we started thinking about what exactly is error in our case. And so we had a team of researchers and we were having these discussions about what was the most meaningful error to try to reduce. Generally, I was just thinking about root mean squared error. Reducing that at subseasonal lead times could be great, but some folks noted that we were more interested in anomaly correlation coefficient, or perhaps we should only focus on reducing errors over land areas because that's where we really care about our forecast skill because of humans and so forth. And others were more interested in reducing biases associated with some mode of climate variability, given that teleconnections associated with that could yield potentially improved predictions at longer lead times. And so we ended up arriving at this realization that there can be competing objectives in our bias correction task, where certain team members may prioritize a certain objective and others may have another objective, and these may indeed be in conflict with each other, where we can't improve one objective without worsening the performance of the other objective. And so that, of course, we refer to as the Pareto frontier. And so in this case, we ended up saying, okay, instead of focusing on just picking one objective to improve, or combining objectives so that we don't really know which one gets prioritized all the time, we decided to keep them separate and work in a space of multi-objective optimization, where we would actually work on finding models that are optimally located along the Pareto frontier of these different objectives. So we ended up choosing 3 objectives, and we use these for our hyperparameter grid search for our bias correction neural network. And so in this case, we're focusing on reducing mean squared error for all samples over land only. And then we also decided to focus on reducing mean absolute error and making sure that we were improving individual forecasts, so that our improvements for bias correction were actual improvement to the respective forecasts, if that makes sense. In other words, instead of trying to get an improvement in mean absolute error or just total mean squared error, and learning big magnitude errors and correcting those, we wanted to say, every time you look at a forecast for CESM, try to improve it a little bit and do this consistently. And so that was what this was focused on. And then we were also interested in improving the sharpness of our forecasts, so that, for example, if we think about the forecast produced by a GCM, a general circulation model, it might be very smooth if the horizontal resolution is very coarse, such as at 1 degree. And if we have an ensemble mean, that's also going to be pretty smooth, just as a function of it being an ensemble mean. And so we decided to prioritize making sure that our coastal regions and our topography or terrain that were like mountains had some sharpness features. So in computer vision, sharpness is the horizontal gradients of associated values in your image, not the sharpness in forecasting for weather, which is a totally different meaning. But here we're focusing on, again, improving that horizontal resolution of our sharpness in our forecasts. And so we ended up arriving at this situation where we have these 3 competing objectives, some of them more competing with others, and said, let's find the bias correction models that try to perform as well as possible along this intersection of our objectives. And so we took just an image to image model. Here I'm showing generally a backbone UNet architecture, and I am allowing a hyperparameter grid search to occur and decide how many input features we should have, what should they be to generate an improved forecast or bias correction, and number of layers and so forth. And so we ended up running a number of studies. Here I'm showing one of these studies that had a over 1,000 trials. So these were over 1,000 trained machine learning models with different hyperparameter configurations. And essentially it identified that there were 53 models along this Pareto front of 3 objectives. And when we took a look at what the hyperparameter grid search found, in this case, it was a genetic algorithm that was performing this search. And we found that there were different architectures that were skillful at this bias correction task. Generally, the UNet was the most frequent out of those 53 models, but there were also some models that had attention mechanisms built in them, and those ended up performing well in other scenarios. And so this was exciting to see, just a sort of more diversity in image to image bias correction models. And regarding training losses, there was also something that surprised me, where the Huber loss was identified most frequently as being the most skillful training loss for this bias correction task, as opposed to some of the other, perhaps more common ones, such as mean squared error. And we can take a look at where these simulations land in terms of the Pareto frontier. And it turns out that it's pretty clear to see that the biggest tension in this Pareto front is between the sharpness metric or objective and simply mean squared error or mean absolute error. And that is true whether it's over land only or whether it's global in scope. And so this makes sense because the more sharpness and detail you have in your forecast, from a computer vision standpoint, it's likely going to result in a reduced or in a worse mean squared error. And so there are a couple of advantages to this approach, it being particularly that we don't really have to compromise on the objectives that we have, even if they are in direct competition with each other. We can actually leverage these multiple objectives to perform a thorough hyperparameter grid search. And a con, though, of course, being that it's very computationally expensive. And how do we even communicate what this multi-objective spread means to a stakeholder at the end of the day? So these are just questions that we're thinking about as we move this forward. I will say we did have another collaboration that emerged from this, being exactly what does sharpness mean in a computer vision point of view, specifically for AI-generated meteorological imagery. And I provided an example of what I mean by this mountainous terrain and complex coastal features, and trying to ensure that we can improve the sharpness. So here, these lighter colors in CESM2 show that we have less sharpness as compared to reanalysis, which is also pretty smooth. But we can actually address this and fix this using a number of metrics that we introduced in this publication, which is currently under review. Otherwise, still a lot more work to do. For example, exactly how do we compute ensemble spread, and what does this mean for us in our multi-objective setting? And just to quickly summarize some of the different key points from the presentation I shared, one being that unsupervised machine learning is quite flexible and actually can allow us not just to uncover patterns, but to also benchmark or evaluate the skill of our physics-based models as compared to observations. And we can also devise experiments where we can assess where predictability comes from. And lastly, of course, having multiple definitions of error can be leveraged for bias correction in a multi-objective setting. So thanks again to the team that I get to work with and all collaborators that have played an important role in these studies. And with that, I'll go ahead and stop talking and take any questions if there are any. Thank you so much for your attention.
Thank you, Maria, for this talk. Please come up with all your questions for Maria now. And while people do that, I'll start asking some things of my own. So for this Pareto front evaluation, the sort of the criterion to select models from that is the models that are on the Pareto front, right?
One more time, can you ask that again? Sorry.
The way you evaluate the models in this last study is that the models that are on the Pareto front, those are sort of the good models, right?
Correct. That's what I'm claiming are the good models, although they may not be that good if you're looking at just one metric. It's just as,
Exactly. Exactly.
yeah.
And have you considered sort of correlated this with I don't know, human expert evaluation or something?
Yeah, that's a great point. I would love to move this into a more let's say operations type setting where we have actual metrics that were devised by, let's say, forecasters and what they need most and focus on improving that for them. Because in this case, it was just kind of a bunch of researchers being like, what does error mean to us and what do we care most about? Which is fine, but I think it'd be more meaningful from a true stakeholder perspective, and having them sort of drive the priorities, I would think.
Mm, mm.
Yeah, this sort of wasn't even really the original point of the study. I thought it was going to be quite straightforward.
Yeah. Do we have questions from the audience? I have some more though. So with the you talked about the ensemble realignment, um, and you were talking about the fact that that on a certain time horizon you had less divergence of the different ensemble members. Was this something that you could see consistently over different data sets or on different data points? On the slide, it
Yes.
looked like you had one specific date for this.
Mm-hmm. Yeah, so it can be a bit challenging to visualize multiple cases simply because the ensemble realignment may not happen at the same lead times, and this was true for different weather regimes and different times of year. So there is a table I put. I don't know if it's in the appendix or supplemental in that study containing a number of cases where this occurred, but they were not the majority, or like it was less than 20% of the forecast. And again, some of them were accurate, but some of them were not. So I couldn't really identify sort of a systematic pattern or reason for the correct ones. Sometimes it was associated with MJO, sometimes it looked more tied to ENSO. So they were really diverse in terms of when they happened. But I think for me personally, it was just interesting to kind of think about patterns propagating across the Earth system and sort of yielding more skill even as those patterns propagate in their respective regions, if that makes any sense, which
Mm.
may be kind of silly that I didn't think about it before, but it was I finally kind of realized that seeing that in this weather regime uh framework.
Interesting. Um,
Mhm.
when you do predictions with the CESM2 model for 46 days, is that auto-regressive predictions then?
The CESM is physics based, so it just computes like the Navier-Stokes and all the other equations and
Okay.
forward in time. Um, the bias correction work would be taking the CESM at the lead time of interest. So wouldn't even be autoregressive, although we could frame the experiment in that way. But we ended up focusing on just the lead times that are used for subseasonal forecasting, which would be like the entire week 3 and the entire week 4, as opposed to like daily fields.
Right. Cool.
Mhm.
Um, and you were talking about uncertain quantification using ensembles. Uh, could this be done with Monte Carlo dropout?
Yeah, that was so initially we were thinking, okay, you can just do this with Monte Carlo dropout. But the challenge with that was that we couldn't really disentangle the different sources of uncertainty. So we couldn't
Mm.
really ask, is it aleatoric? Is it epistemic? And that really limited us, I think, more so to like the machine learning model uncertainty, perhaps, because we're doing dropout as like parts of the network. Um, but we did do a comparison to Monte Carlo dropout in the paper as
Right.
a yeah, just to show that.
Cool. Thanks. Do we have some final question from the audience?
Thank you for all your questions. Oh, well.
Yeah. Yeah, thank you for this interesting talk. I loved it. And I'm sure the rest of the people did too. Sigrid has a question.
Yeah, I was curious about, you showed pretty early on about aleatoric and epistemic and sort of dividing up where the uncertainty came from. And I think it looked like quite a lot of it was epistemic. Did you sort of get a feel for like, maybe I'm remembering wrong, but did you get a feel for like how much better we can make it? Like where we're going to um just not be able to do anymore?
Yeah, great question. Let me pull that up. So, yeah, there's an important thing I'm realizing that I did not mention, which is that when you see a large value in epistemic uncertainty, you should disregard it in the aleatoric, meaning when this is high, which I'm noticing just now, the color bar isn't here. High values are red in the epistemic map and the same for aleatoric. And so here you would say, okay, I can't really trust the aleatoric uncertainty out here because I simply haven't seen enough examples of this. And in this case, it's a toy example where we just dropped very high values of temperature in this one sample to illustrate this. But when you're seeing higher values of epistemic, and you can see perhaps not high values, but it's a bit higher out here as well, and like towards Alaska and British Columbia, and looks like down here as well in the Gulf of Mexico coastal region. So it is possible that that some of these other values in aleatoric should be taken with more caution. But this one out here for sure, we would say, okay, I can't not trust this. We did not take the work further in terms of increasing the samples of the epistemic to try to reduce it. But I do know of work that others have done to do this for things like remote sensing precipitation. I think they use Bayesian neural networks, and I'd be happy to follow up after if you're further interested with that publication. And so they were able to take samples of scenarios where they needed more data and provided that to sort of tamper down the high epistemic uncertainty. So that would be one potential use case for the value of this. Yeah,
Great.
and also simply for the training.
Thank you.
Thanks for that question.
One question on the aleatoric and epistemic uncertainty. Like, if you tie in back the other result that you showed, that the variability of outgoing long wave radiation impacted the uncertainty, like which bin will that fall into? Would that be an inherent uncertainty or?
Hmm. Yeah, I see what you're asking. Quite interesting question.
Mhm.
Hmm.
Or does it
Yeah,
come?
that
Yeah.
go ahead. Go ahead.
No, or does it come down to the fact that if we are unaware that this kind of event is happening, it will be categorized as an unknown?
Yeah, I would think, I mean, there's going to be probably sources of both. One, because we only have a 20-year hindcast in that study,
Hmm.
there's only going to be so many combinations of modes of climate variability that and their propagation and their create, certain lead times and so forth. And another thing to note is 20 years, but that each forecast was initialized once a week. So that also further reduces the sample size. So there's definitely an epistemic component there, but I would say there's also aleatoric uncertainty there because we're looking at convection, and that's going to be high magnitudes or large magnitudes. So there's going to be just simply any placement that's slightly off is already going to be a source of, is going to be contributing to the aleatoric. It's just hard, it's just challenging to get the placement of convection perfectly right and its propagation speed. So it's going to be, I would say probably in that case, just not satisfying, but yeah.
Yeah, it kind of makes sense. I think like the model only, the quantification model only sees the window which is trained on, and anything about outside of it's an unknown. Does that make sense? Like, yeah, maybe so. But
Cool.
it is a challenging thing. Yeah, thanks for the answer.
Thanks for asking.
Cool. One last question. The video that you showed in the intro, I suppose that was you in an airplane that were making some kind of a, I don't know what it's called, not a loop, but the other way around.
Yeah, that was a pilot being more than 6 Gs. So essentially, as I understood it, physics depends, like you passing out on an aircraft will depend on the direction of that vector is pointing. And for example, when we took off, they went like 90 degrees vertical, and that was pointing this way. And so that was fine for me. But in that maneuver, it was pointing down. And so that drew blood from my brain down and triggered a pass out. But that was me, yeah.
Wow.
Yeah, many years ago.
Wow.
Yeah, they think that's funny to do to folks they take on the plane, I guess.
Yeah. Yeah. Right. Amazing and scary.
Yeah.
So I think we will conclude this seminar. Thank you so much for this interesting talk. Next week, welcome back, everybody. We'll have Abdul Shamala, who's a PhD student at Queensland University of Technology. He'll be talking about optimizing green infrastructure for climate resilient cities, AI-driven approaches to urban cooling. So that will be next week on Thursday. Thank you so much.
Thank you. Bye.